Okay, hi everybody, and welcome to my taster of the workshop. The workshop is about static reflection and C++26, a topic that I'm very enthusiastic about and also want to share with the wider C++ community. So who am I? My name is Koen Sameen. I'm program coordinator for game development. So my activities with regards to C++ are mainly about games and graphics programming. So I'm very active with compute shaders as well. But I have encountered reflection at CPPCon this year, and I was instantly triggered to do something with it. So what you will see in the taster is a general overview of reflection. I will go a bit faster. It's not the intention to do a speedrun of the entire workshop, obviously. I got some gobbled starting code. If you're following live, you can find those URLs in the Discord chat. And if you're watching later, you will see them in the description. So a couple of short examples of what reflection can do. I will try to do a bit of live coding, which we will also do during the workshop, but in more bite-sized chunks. And I'll also discuss what use cases we will cover during the workshop. And also a very powerful new functionality in C++26 reflection is that meta substitute. And that's really a game changer. Without the token injection, it is possible to do a lot of stuff as well. As you can see, and I will explain this at the end of this taster, you can meta compile, I would say, a program and run it in your program. So it's compilers and emulators all the way down. So what is reflection? The main thing about reflection is that it works at compile time. So you have your C++ code. Some templates are instantiated, as we'll cover in the workshop, of course. It depends where you reflect stuff. You can only reflect things that are visible to the compiler at that point. So you're doing it at compile time. Some people call this the cat ears operator. It's the reflection operator. There's a lot of discussion in the paper about reflection, why they chose this syntax. But the main thing is you reflect something, can be an object, a type, whatever, and you get a stat meta info object back. This is an opaque object, so which means that basically everything inside of this object is hidden, and you call functions on this object to get something else. So for example, for a struct, this might be the data members of the struct. So you access some additional information. This might be enums. In the talk earlier at CPP Online, there was discussion about enums and how to get the string representation of the enum. For example, you get functions, data member, even annotations, which is also a new thing in the form of custom annotations that you can also use during reflection, which is also something that we'll cover in the workshop itself and not during this taster. Then the special thing is it's a cycle. You reflect something, probably with the goal of reflecting it back into the C++ code. This, of course, can trigger a loop because that new code might also trigger new instantiations of templates, which might contain, again, reflection code. So if you don't do any reflection anymore, that's the end of it. But it could be that you start to loop again with new code that was discovered during template instantiations, for example, and that code might again contain the reflection operator. You leave the reflection world with a couple of functions, like you can get the identifier of something. For example, here, this could be a member velocity of a particle struct. You will notice I use a lot of concepts that are common in game development, but not in a very deep way, just as an example. So here we have a string view that gives us the name of the data member. And then you might ask, like very common in Java or C#, if you have a string, can we get back into reflection land? And it is possible, but you have to change your way of thinking. You have to start from the C++ information and create, in fact, some code with template for an if const expression to check which one or if any member matches that string. So that's a bit a different way of thinking with regards to languages such as Java and C#, where you can start from a string and query anything everywhere. With C++, it's during compilation, so you can only use what you know during compilation. Okay, let's go to the live demo. A bit stressful, of course. So what we're going to do is we have a struct particle. We have a float x and y, very common. We also have an ID. There might also be an enum in there with the state of the particle. And we just have a main function. We're going to reflect the struct. We're going to use template for an if const expression. During the workshop, I will go into more detail and give you some separate examples of these syntax elements because they might not be familiar to you, and we'll reflect the members of a struct. We'll go with the particle struct and reflect it directly, but it is very easy, in fact, to make a templated version that works on any struct that you might want to reflect. So let's go to Godbolt, good old Godbolt, which is very handy here. There is the reflection branch of Clang, which is available, and you have to use the flag -f reflection latest to use this thing. So let's see. Main thing that is easy to forget is that you have to use const expression. If you get something from the reflection world, it's typically going to be a const expression. So we have a particle info, which is a reflection of particle. So let me just widen this middle a bit. Okay. So we have a reflection of particle. You see that the code still compiles. And we're just going to print out the identifier of that info. So that should give us the name of the struct itself. And we'll have to wait a little bit for the compilation. And in fact, here you see particle being printed out. So during the workshop, I will also explain how to work with Godbolt. If you haven't done that before, it's pretty easy. Main thing is not to forget to set the compiler to the right one. And also you have to sometimes enable execution because it typically only compiles the code, and also activate the output window. So let's create a particle now. So there are 3 members, and we will reflect the field X. So this is a stud meta info object, and this is also sometimes the little tricks or something that you need to know. So it's kind of a namespace like lookup of the X field within this particle. Okay, I already have errors. I of course forgot to use a variable name, and we can then also output that. So we go with the out identifier of again. That's one that identifier of the X field, and we put a semicolon in there like you would for a JSON output. And then this is something that we'll do a lot during the workshop. It's something to get used to. We splice that field back in. Of course, here it doesn't make a lot of sense because, we can just directly call X, of course. But okay. Voilà. And we have the output, X is 4. Okay. So that's kind of easy. If you want to reflect all the members, like suppose you want to serialize something, so we just ask all the members. We have to create a context. So this is a requirement. So a stat meta access context, and it's an unchecked one. So why is this important? Unchecked will just give you everything that's visible to the compiler itself. So there are other contexts that are a bit more restrictive that might give you only what's visible from a certain scope. So we get the members. In the interesting talk at the beginning of CPP Online, there was discussion about this specific thing. So it's a bit strange at first because many people are not used to thinking about, okay, this is code that will run during compile time. So there are a bit other rules that are in place. Main thing is that in const eval functions, you can create dynamic memory, but it will be gone when your program runs, because that dynamic memory is part of the compiler's heap, right? And the compiler is done when your program is compiled, so it's gone. So you have to store the information that this function, the non-static data members, generates before you store it into another member. Okay, so we have particle again, and we have to supply the context. Okay. I got a squiggly there. Did I make a mistake? No, I did not. So we could use this already to output something JSON-like. So just a curly brace, new line. Again, something to get used to is the template for. So we have a const expression. I'm using auto a lot because it's new API. Stat meta info is going to be pretty stable, but still it's a bit handier to do it like this. So we loop over the members. The main thing for template 4, we'll do some examples about this, but it's that it's always unrolled. So all the code inside of it will become unrolled. So will become one big chunk of lines. So we can output again some parts of the JSON thing. We output again the identifier of the member and what, so a double quote, the colon between the key and JSON, and we splice. So this is strange at first. We have member info, which describes the member at that point, and we output it. Okay, I forgot the off thing. I'll fix it right away. So identifier off. And this hopefully compiles. Yeah. So here you have like something that we would use to output JSON. Some improvement to do is, of course, there are commas between the fields in a JSON output, but this is already one small demonstration of what you can do with reflection. So, yeah, there's a bit of info here. So let's go a bit further. So slideshow. Okay. So what happens when you go a bit further than most examples that you find is that, yeah, normally a flat struct with only primitive data types is not that common. So typically you will have a data structure. So for example, I moved X and Y to another struct definition. And now we have a struct particle with a vector2f location and an int ID. So if I run this now with the code that I had, I get an error here when outputting this. Why? It's telling me, well, there is no output operator for vector2f, of course. So I'm trying to write that out, but there's nothing there. So what could you do? How can you solve this? Yeah, you could use an output operator and output the vector to f, and that would fix it. Here you can see maybe already the problem. It's not in a JSON format here. So I'm just like using some kind of mathematical notation. You have to do this per type. You have to adapt to whatever format you want to do, but that's not easy with this operator. So, okay, maybe you have to do it some other way, but there is a better way now with reflection. So let's look at it. We are going to visit the data structure with reflection. So we're going to visit all the values and all the members of, or the possible members of those values with a visitor. And the special thing is that this visitor is external. It's not something that you need to define inside the struct itself. So without writing any code in your domain classes, which is important, you can visit them. So, and you can visit them as deep as you want to visit them. And we'll see that in the workshop that with annotations, you can control if perhaps some part of the data structure is not important for serialization or not important for rendering, for example. So you can really control all the aspects of what you're doing. There are a couple of things that we, of course, need to discuss in the workshop. It's okay, we have this function that we call recursively. We have to have some way to test, is this a class or a struct? Is this an enum? We might do different things for a sequence or for a map. So you need to test these things. I guess a flowchart is something that is a little bit old school, but I think in this context, it makes sense to use it to discuss these types of things. So I have a template. It could be the particle that I visit. I check, is this a class? I call the right struct. I iterate over the data members. I write a key, for example, for JSON. And what do I do then? I will have to visit the values of that struct. For example, for an enum, I write the enum. So this is some output. So the output is there. I will talk about this in a sec. And if it's not an enum, of course, there are more possibilities. So you have to extend this if-else structure. Then I assume it's a primitive and I just output it directly. Of course, there are opportunities to create template code with specific converters as well. So what do I do? Visit value? No, this is not correct. Okay, I would have an infinite loop, so this is not right. I have to splice in the members that I get out of my template for. So I have a visit function that is walking through the data structure. So pretty interesting. And then you can go a step further and say, hey, why are we giving an O stream to this visit function? So let's do it a bit more in a pattern kind of way. And we can have a visitor. So you have your visit function. So you have all the infrastructure that walks through your data structure. And then you can have a visitor that gets notified of specific things that happen in your data. Okay, let's look at the time. Okay, I'm doing pretty good. So what can you do with it? When I was preparing this workshop, I had several applications in mind, so serializers. These serializers we will also discuss a bit, but it's a bit trickier because sometimes when you write to JSON, you don't write enough information to read it back correctly. So serializer and deserializer have to be balanced against each other. So I guess it's always easier to write something out than sometimes to parse it back in. ImGui is interesting. So in graphics programming and tech demos, we use a lot of ImGui. I will mock the ImGui functions in Godbolt to ensure that the workshop is only 3 hours. So I don't want to have too many libraries and special cases. I will also show you, there's even a nice GitHub example already of one person that already made a reflection library to automatically bind stuff in ImGui. And we'll create a visitor. So that's the main thing. If you have a visitor kind of pattern with reflection, the sky's the limit with of what you can do with it. Again, an interesting concept is classes as containers. So you store data members in your class by value, and you can reflect on those, and then your class becomes kind of a container that automatically can call functions on the values it contains. Something that comes along with it is to check if the data members of that class are conforming to certain template concept, which is also an interesting check to do. And we'll close off with meta substitute. It's really insane how powerful this function is. So let me just give you an example. What's the idea? You reflect a template, could be a function template, could be a class template, and you instantiate it with custom parameters. Those parameters have to be const expr, but you can just instantiate new template based on some const expr values that might come from a const expr array or from embed, whatever. And I have a demo in the workshop where you can meta-compile. I'll call it meta-compile. I don't know what the correct term is. I guess there's not really correct terminology yet for it. And I'll just meta-compile a tiny stack-based virtual machine as directly executable statements. So this sounds a bit crazy. So if you're intrigued, come follow the workshop. I'll just show you that it actually works. So I have the program here. So it's a simple stack-based program, not very fancy. I have emulation of the CPU with some registers, a program counter, a stack, and a stack pointer. The execute functions will be a template function. So that's important for this substituting to work. You need a template that you can instantiate. And then this is something for the workshop. We'll reflect the execute function. We have some way of getting const expr expressions for the two template parameters. We call substitute. This gives us a instantiation of the template. And then we can store the spliced instantiation into an array of function pointers. So pretty crazy if you think about it. I compile it with O3 reflection latest. And if you run through the program and step through the program and let it run out and get the state of the stack after that program, you get 8, which is, of course, 5. I push 5 to the stack, I push 3 to the stack, I add them together, and then my program ends. Not very special, of course, but it's really crazy that you can compile a program during the compilation of a C++ program. So it's really kind of a inception kind of thing where you have programs compiling other programs, compilers compiling a program. So let's go to the slideshow. So this was the workshop preview. I hope you're interested to follow it for the full length of 3 hours. So there's a workshop at 2nd of April and 25th of May. So I'll be happy to see you there. Thank you and see you later.